Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis. So, today is our first tutorial session. My name is Sri Lakshmi S. I am a research scholar in IIT Bombay in Department of Chemistry under Professor Krishna P. Kaliappan. So, here we are discussing the course of Professor Krishna P. Kaliappan, the Classics in Total Synthesis. Let me share the screen. Is my screen visible? Okay. So maybe we will wait for a couple of minutes more and see whether anyone else is joining, and then we will start the first tutorial session. Okay, so we will be starting the class. Anyway, this tutorial session, all the links and all the slides will be shared to you. This videos will be uploaded in YouTube, and that YouTube video link will be provided to all the scholars and all the students who have registered for this course. So let's start. So before directly going into the problems, first we will see what is the outline of this course basically. Yeah, so before going into the course directly, we will be having an idea of the week's lecture. So, if today I am taking this tutorial, firstly, we will have a discussion on the previous week lectures. So, if you have any questions or any doubts regarding any of the lectures, you can ask. If I am not able to answer that immediately in the next tutorial session, I will be happy to answer all your queries. So, today, so we will be having a discussion on the week 1 lectures first, and then we will try to solve the week 0 assignment questions. I hope everybody has already done that week 0 assignment. Then maybe a few more problems. If time is there, we will be solving a few more problems as well. So, firstly, in the week 1 lecture was almost about the complete overview of this course, the syllabus of this course, which all references we can follow in order to tackle this course, or in order to have a better understanding about this total synthesis and different mechanisms of the mechanisms of the various organic reactions. So, firstly, we saw the syllabus of this course basically contains the introduction to organic synthesis, and then the synthesis of natural products with three membered, four membered, five membered, six membered, and medium sized rings and macrocycles. So, basically, in this course, we will be seeing the total synthesis of different natural products having all these different sizes of rings and different core structures. And also we will be seeing more than one approach to a particular natural product. So how different group have approached the natural products in different ways using different key reactions. So through that we will also get an idea about how to approach a natural product and how to devise a retrosynthetic strategy. So that is the main aim of this course, and as you know, this is mainly aimed for MSc and PhD first year students. Then, yeah. So, organic synthesis is actually a bridge between the medicine, biology, chemistry, and materials. So, it is very important in all the fields of sciences. And total synthesis, which is a field in organic chemistry, is the ultimate in synthesis. That is, it is complete synthesis. We are synthesizing a natural product which can be isolated from plants or bacteria or any living organisms present around us. So that natural product which is already available in nature, we are synthesizing it in the laboratory. So that is the ultimate in the synthesis. So as we have seen in the lecture, there are basically two type of organic synthesis: target oriented synthesis as well as methodology oriented synthesis. So target oriented means we will be, as I said now, any natural or non-natural products, we will be having a specific target. So we have a molecule, so that molecule is our target. So we will be designing a retrosynthetic strategy for synthesizing that target molecule, and based on the retrosynthetic strategy we will begin our forward synthesis. And on the way, we will be seeing different types of reaction on sometimes whatever we have designed in the retrosynthetic strategy may not always work. So in that case we will have to modify our strategy or completely change the strategy sometimes to tackle the natural product or any target which we are planning to synthesize. So that is target oriented synthesis, in which we will be having a particular target, and we will be in many steps we will be achieving that particular natural product or non-natural product. Now another type of organic synthesis is methodology based synthesis. So methodology based synthesis means we will be this is actually it will provide an aid to target oriented synthesis. That is, in methodology based synthesis we will be developing reagents, catalysts, or synthetic strategies or synthetic techniques which can be utilized somewhere, like which can be utilized in this target oriented synthesis. So whatever reagents, catalyst, some reagents we will prepare, and what are the utilities of that reagent, what are the limitations of that reagents, where all these reagents can be applied, where all it couldn't be applied. So these things we will be studying in methodology based synthesis. So in target oriented synthesis, okay, which methodology based synthesis can we apply in the target oriented synthesis, we can see through by going through different methodologies. So that is the classification of organic synthesis: target oriented synthesis and methodology based synthesis. I hope it's clear. In between, if you are having any doubts or questions, feel free to ask. So that was about the lecture one. And in lecture one, we have also seen different natural products having different types of or different membered rings. For example, illudin is a natural product which is having one cyclopropane ring, where another natural product FR900848, which is having five cyclopropane ring. Then N-andric acid is having one cyclobutane ring, which is four membered ring. Same with penicillin, tyramycin, these all are having cyclobutane ring. Then prostaglandins are having cyclopentane ring. Two cyclopentane rings are present in prostaglandin. Then we have also seen what are tricunanes, angular tricunane, linear tricunane, propylene type tricunane, and examples like isocoamine, which is an angular tricunane, herostine, which is a linear tricunane, modifane, which is a propylene type tricunane. And then we have seen examples for natural products having six membered ring, like longifolin, which is having one six membered ring, two five membered ring, and one seven membered ring. Then carpanon, which is having four six membered rings, and then gibberellic acid, then several steroids examples we have seen which is having six membered rings like progesterone, estrone, cortisone, testosterone, then alkaloids like perhydro trionicotoxin, methyl homosicoda, phenylphthalate, dendrobin, lysergic acid, quinine, reserpine, yohimbine, morphine, strychnine, galantamine, taxol. So a variety of natural products, including steroids, alkaloids, are having six membered rings. So that was about the basic content of the lecture one. Now, moving to lecture 2, we have seen several technical terms. So, it was basically the introduction to several technical terms in the lecture 2. First one is organic synthesis. We all know what is organic synthesis, basically synthetic organic chemistry. So we will be dealing with reactions, mechanisms, sort of things in this organic synthesis. And what is total synthesis? So there are in organic synthesis there are several type of synthesis, or if in target oriented synthesis we can say there are several type of synthesis. So in target oriented synthesis itself we can have total synthesis, semi synthesis, partial synthesis, formal synthesis. So, what is the difference between these different types of synthesis? Everything is synthesis only. Then why we are calling it with different names? So, talking about that, the first one is total synthesis, which, as I said, it is the ultimate in organic chemistry. That is, we are planning for the complete synthesis of a molecule, whether it be a natural product or whatever. We have a target and we are planning for the complete synthesis of that molecule, the target molecule, starting from simple commercially available starting materials. So that is known as total synthesis. That is a complete synthesis. The chemical synthesis of molecule from relatively simpler starting materials. Now the next one is semi-synthesis. So semi-synthesis means somewhere we are missing something from the total synthesis. That's why we call it semi-synthesis. So semi-synthesis means we are starting from an advanced intermediate. Like for some molecules, the advanced intermediate will be already available in nature in some form. So we will be isolating that from nature and we will be starting the synthesis from that intermediate, advanced intermediate, so that in one or two steps or two, three steps maximum, we can reach the target molecule. So that is semi synthesis. Now, what is formal synthesis? Formal synthesis is previously what is already a molecule is already synthesized. So what we are doing is whatever reported literature is there, we are choosing an intermediate from that literature and we are proposing an alternative strategy to synthesize that particular intermediate. So we are not completely doing the synthesis, but we are synthesizing it up to a particular intermediate from which the synthesis total synthesis is already known for that natural product or that molecule. So basically, what we are doing is we are synthesizing an advanced key intermediate from which the target molecule could be easily achieved. So that is formal synthesis. Now, talking about partial synthesis. Partial synthesis means we will be dividing our natural product into several fragments, and out of these fragments, we will be choosing one fragment and we will complete the synthesis of that fragment only. So, that is known as partial synthesis. So, in organic synthesis itself or in target oriented synthesis itself, there are several kind of synthesis. Total synthesis, where we are, which is the ultimate of synthesis, we are completely synthesizing a natural product or a non-natural product, or we can say a target molecule starting from commercially available simple starting materials. Semi synthesis means we are starting from an advanced intermediate which is available in nature, and in two or three steps we are finishing the total synthesis of that natural product. Formal synthesis means we are starting from commercially available simple starting materials and synthesizing a key advanced intermediate from which it is already known, that is literature have been already published for the total synthesis of that target molecule from that key advanced intermediate. So we are developing a new method to synthesize that key advanced intermediate. Now, partial synthesis means we will be fragmentizing our natural products, and out of that fragment, we will select one particular fragment and we will finish the synthesis of that fragment only. So, we are completely not synthesizing the molecule, but we are partially synthesizing the molecule, um, partially synthesizing a part of the molecule. So, that is known as partial synthesis. Now, we have also seen several examples, or one or two examples for each of these classifications: total synthesis, semi synthesis, formal synthesis, and partial synthesis. So, for semi synthesis, we have seen Taxol. So, Taxol is a drug which is used in the treatment of ovarian breast cancer, and it is isolated from the bark of Pacific yew tree, which is a very slow growing tree. So if we have to isolate this natural product from the bark of the tree should be grown into its full size, then only we can isolate it from that bark of the tree. So it is a very slow growing tree, and the amount which we can isolate from one single tree will be very less. So another compound is there, which is 10 deacetyl baccatin 11. So that will be in 2 3 steps. Some acetylation and side chain attachment will give Taxol. And this particular compound, 10 deacetyl 11, is isolated from the leaves of the same tree. So what is the difference between isolating from bark and leaves? So for isolating from bark, we need to cut down that tree completely. But for isolating from leaves, we don't need to completely cut down that tree. We can isolate from the leaves, and the leaves will grow back again, and again we can isolate and synthesize this Taxol. So from this, many derivatives of Taxol could be made. No need to cut the trees also. So that is semi-synthesis. From an advanced intermediate which is already available in the nature, we are synthesizing the natural product or a drug molecule. Now, an example for partial synthesis is discodermalide. So, discodermalide is divided into four fragments, and separately the synthesis of each of these fragments is reported. Now, our group, that is Professor Krishna P. Kaliappan's group itself, has reported that the formal synthesis of vinegrol. So, we have synthesized up to a key intermediate from which already the synthesis have been reported by other groups. And we have also seen what are the basic requirements and need for organic synthesis. So, synthetic chemist is like an architect plus a civil engineer. So, we should be knowing a variety of reactions, and we must be having some amount of creativity. Then only we can play with the number of steps and which reagent or which reaction to use. Because if considering, for example, for oxidation reaction, there are several reagents available, several reagents could be used. So out of that reagents, which will be suitable for our particular starting material or our particular reactant? So there we have to have a little creativity. Maybe some amount of alterations in our scheme can reduce the number of steps towards the total synthesis. So that's why we need some amount of creativity in doing total synthesis. Then, yeah, what is the need for synthesis means we need to discover new chemistry, of course. Then, of course, after completing a natural product, the amount of scientific excitement and satisfaction that we get is out of the world. Then, and in previous days, in early days, when the spectroscopic techniques and other techniques were not so much prevalent, in that period, the total synthesis was one of the method which is utilized for confirming the structure of the natural product which is isolated from nature. So that is another need for the synthesis. And even after the discovery and this NMR and other spectroscopic techniques have come into use, then after that also, now also some molecules, some natural product synthesis is helping in confirming the structure. Sometimes already reported structure is also being modified after its total synthesis have been done. Then of course it's utilized, its usefulness we know in medicine, biology, materials, and everyday life. So that was about the second lecture, which was about the introduction to some technical terms. Now, moving to the contents of third lecture. So, in the third lecture, we had an idea about the history of organic synthesis and what is retrosynthesis, these kind of things. So, the first synthesis of a natural product was not a natural product. The first ever synthesis was done by Waller Group in 1828, which was the synthesis of urea. So, that was the first ever synthesis done in the history. And the term synthesis was coined by Kolb in 1845, where he synthesized acetic acid. Then a first other 1890 glucose was firstly synthesized in lab by Fischer's group. Then in the 20th century, tropinone was synthesized by Willstatter, then Robinson, then quinine was synthesized in 1944 by Woodward. Woodward itself synthesized cortisone, strychnine in 1951 and 1954 respectively. Then penicillin V was synthesized by Sheehan in 1957, longiflorine by Corey in 1961, and Corey has reported the synthesis of gibberellic acid in 1978. So initially they have what they have done is for completing the total synthesis they used to select simple target molecule, so that whatever readily available starting material is there, in a few transformations we can get that natural product. So that was the initial target of in the total synthesis. So now coming to the retrosynthesis. So we know if we have a starting material A, we are synthesizing a product B. So that is forward synthesis, or we can say synthesis. So A to B is synthesis. Now retrosynthesis means reverse of the synthesis. That is, we are planning for the synthesis of B from A or from whatever starting material possible. Firstly, we will select the target molecule, and then we will decide which starting material can be used to get this target molecule, that is retrosynthesis. So for that, what we need, we have to disconnect that particular target molecule into several bond by several fragmentation of the bonds or cleavage of the bond to get the starting material. And that particular compounds or that particular fragments which we get from the fragmentation of various bond is known as synthons. And synthons are the actual synthetic equivalents or actual substrates. Synthetic equivalents are the actual substrates which we use for the synthesis. Forward synthesis is known as synthetic equivalents. For examples, if we see a cyclohexene ring in a natural product or anywhere, the first thing it will come into our mind is, okay, the cyclohexene can be prepared from a Diels-Alder reaction of butadiene and some dienophile. So that is the first thing that will come into our mind. So we have this target molecule and we are designing backwards, like what can be done to get this target molecule. And so the synthesis basically involves two stages: analysis as well as synthesis. Analysis means selecting starting materials, identifying which group to break or which strategic bond disconnection to be done, and we have to repeat this disconnection to reach the starting materials. So out of this, at least one of this disconnection should be novel for our retrosynthetic to be what to say, to be more novel in the literature, which it should not be already known in the literature. So then we have seen that there are basically two types of synthesis, or we can say we can synthesize, complete the total synthesis of a natural product either by linear way or by convergent way. So linear way means we are synthesizing directly through step by step we will be going, and we will be achieving our target molecule or our natural product. Convergent way means we will be synthesizing two or more fragments and somehow we will be coupling or joining these fragments to get the natural product or our target molecule. So that is known as convergent synthesis. So that is the two types of synthesis: linear synthesis as well as convergent synthesis. Then in the lecture 4, we have seen the total synthesis of illudin M and C. So these are the structures of this illudin M and illudin natural products. There are various derivatives for this illudin class of natural product. And here we have also seen what are the standard methods which could be used for preparing a cyclopropane ring in a natural product. So while devising a retrosynthetic strategy, it is very important to know how to construct each of these rings in the natural product. So here we have seen in this lecture we have seen how to construct cyclopropane ring. So the standard methods to make three member ring are SN2 displacement of a 1,3 diketone or a beta ketoester. Then we can use Simmons Smith reaction. Then by using diazo compounds we can do cyclopropanation, or by using sulfur halides we can do the cyclopropanation reaction. And then about the illudins, we have seen it is having biological importance as well. It is having selective toxicity for the tumor cells. So as we can see in the structure, it is having a six-membered ring, a five-membered ring, and a three-membered ring. And we have also seen how is it acting, what is its mechanism of action. So mechanism of action is in such a way that it will act like, if we see, there are several Michael acceptors in this molecule. So this can act as a Michael acceptor. So a nucleophile can attack at this position, which will result in here OH kind of thing. And then another nucleophile can attack at the cyclopropane ring and it can open the cyclopropane ring. So as a result, after this nucleophilic attack, what will be resulting is an aromatic six-membered ring. So that's how that formation of that aromatic ring is the driving force for this reactivity of this illudin molecules. So yeah, that is the mechanism of action of this illudin. Then we have seen that this illudin M was first synthesized by Kintos group in 1994 by carbonyl halide for 1,3 dipolar cycloaddition. Then we have seen several examples for 1,3 dipolar cycloaddition. What is a 1,3 dipolar cycloaddition reaction? What are the various substrates using which we can do this 1,3 dipolar cycloaddition? So some examples are carbonyl halides and nitrile oxides. So we will be having a dipole and a dipolarophile. So it will be forming a concerted reaction will happen and it will form a five-membered ring. So that is 1,3 dipolar cycloaddition, which is basically 3 plus 2 cycloaddition. So some of the examples where we can use this 1,3 dipolar cycloaddition, or some of the dipoles which we can use in this reaction include this allyl anion, nitrile oxides, carbonyl halides. These are the examples of the dipoles which we can use in the 1,3 dipolar cycloaddition. Then in the last lecture of week 1, we have seen the total synthesis of this FR900848. So if illudin was having one cyclopropane ring, this is having 1 2 3 4 5 cyclopropane rings. So we have seen how these 1 2 3 4 5 cyclopropane rings are constructed in this natural product. So this molecule was isolated in 1990 by Yoshide from the broth of fervent verticillium, which is a fungus, and it is having 5 cyclopropane rings, and this molecule is known to show antifungal activities. And the major synthetic challenge associated with the total synthesis of these molecules are, it is having 14 chiral centers. Then as I already mentioned, it is having this 5 cyclopropane rings and this 3 double bonds which is in the E configuration. So Barrett group in 1996 has firstly achieved this natural product. So where he utilized the Simmons Smith reaction, which is basically the for the construction of this cyclopropane ring using zinc carbinoid. So, through this zinc carbinoid. And several asymmetric strategies have also been developed for the construction of the cyclopropane ring using chiral boronic catalyst, and sometimes in the substrate itself we will be having a directing group which will direct the incoming molecule towards its own spatial orientation, so that can also affect the chirality of the molecule or chirality of the incoming group. So that's how we install the chirality in this natural products. So that was the lecture 5, which was about the total synthesis of FR 900848. So if you have any question about whatever we have discussed till now, you can ask about the lecture contents. Can anybody of you please respond? Rohan, are you here? Am I audible? Okay. So, if there is no questions regarding the lecture contents, and we have also seen that some of the references which could be followed for the better understanding of this topics, which is basically EJ Corey's textbook of in logics of chemical synthesis, then classics in total synthesis by Casey Nicolau, then organic synthesis disconnection approach by Warren, modern organic synthesis workbook by Zweifel and Nance, some modern methods of organic chemistry by Caruthers, domino reactions in organic synthesis by Teets, then advanced organic chemistry volume 2 by Carey and Sandberg. So these are the some of the references which you could follow for the better understanding of the topics as well as the mechanisms. So now we will move ahead with the discussion of the problems. It will be better if you can respond. So, the correct structure of monoterpenes, camphor and alpha pinene respectively are. So, four structures are given here out of this, which is the structure of camphor and which is the structure of alpha pinene. Hello, am I audible? Okay, so the correct answer is camphor. This is the structure of this camphor. This is having a bridge system like this. So, out of this two, this is the correct option for this structure of camphor. And the structure of alpha pinene is this. So, this is this one. So, the correct answer is 1 and 4, option 1. Now, the second question is identify A in the following reactions. So here we have to find which starting material can be used, where we are doing this, treating that compound with NOCl in pyridine and then H3O plus, then swan oxidation to get this compound. So out of this four options, which starting material can give this target molecule? I will give you some time. So if you know the answer, you can just write down in the comment box, or you can respond and then we can discuss the mechanism. Okay, we have only one participant now, so it will be good if you can interact.
I think it's the second option.
Okay, we will try that. Can you explain what is the first reaction and what is happening?
Basically, we're just adding that CHO. So I think it could be third because we can easily do like OH2CHO.
But we are using here NOCl and pyridine. So it is a named reaction, right? Can you recall which
Yeah,
named reaction it is?
I don't recall.
Okay, have you heard about Barton reaction?
No,
Okay, so you are MSc or PhD?
M Tech.
Okay, okay. So, Barton reaction is actually, this is Barton reaction. So, when we are treating an alcohol with this NOCl and some base, here they are using pyridine, it will form this ONO kind of derivative. Then when we are treating it under light, or when we are exposing it to light, what will happen? This bond will cleave, homolytic cleavage of this bond to form O radical and NO radical. Then what is happening? From the delta position, that is, this is alpha, beta, gamma, delta. From the delta position, one of the hydrogen radical will go and combine with this oxygen radical. So here will be another radical which will combine with this NO radical to form this particular intermediate, which can exist in this form as well. So that is Barton reaction. So firstly, whatever alcohol, we will be having an alcohol when we treat it with the base and this NOCl, it will form this ONO kind of bond. Then we are exposing it into photochemical condition, this alpha, beta, gamma, delta. Delta hydrogen radical will be forming, and that delta hydrogen radical will combine with this oxygen radical to form here OH, and then the resulting radical here will combine with the NO radical to form this one, which can exist in this keto form as well, and these are the tautomers. So that is the first product which we will be getting. So whatever starting material we are using here, firstly what that OH will be converted into ONO, and that ONO will be cleaved, and O radical will form and NO radical will form. Then from the delta hydrogen position, hydrogen radical will be forming, and that radical will combine with this NO radical. Then in the second step of Barton reaction, what will happen? If we hydrolyze this, we will be getting ketone. Ketone or aldehyde, what will be forming? We will be getting that particular carbonyl group if we are hydrolyzing this hydroxylamine, we can say. Then last step what they are doing is swan oxidation. Swan oxidation means what? Oxidation of primary alcohol into aldehyde or secondary alcohol into ketone is swan oxidation. So if we consider this first option here, if yeah, so here in the first step it can form here O NO. And here is one methyl group, and here is the stereochemistry is already fixed. Here also stereochemistry is fixed. So then what will happen is when we will expose it into light, this ONO bond will cleave and delta hydrogen radical will be cleaving. So delta means this is alpha, this is beta, this is gamma, and this is delta. So from this, here is CH3 group. So three hydrogens are there. So from that, one of the hydrogen radical will cleave and it will combine with this oxygen, and this NO will go there. So we will be getting here OH will be there. And when we are hydrolyzing this directly, I'm writing it as aldehyde, so this will be aldehyde. So this will be the product after this two steps. Then what we are doing is swan oxidation. So swan oxidation, only one alcohol is there, so that alcohol would be converted into ketone, so we will get our product. Now if we consider the stereochemistry of the reaction, so for this Barton reaction to occur, whatever like this oxygen hydroxyl group is in which position, in the same position only that hydrogen radical abstraction is also possible. So if OH is above if OH is above, that hydrogen radical should be abstracted or can be abstracted only from the above position. So when you said the second option, here problem is that this is alpha.
Below.
Yeah, so
Yeah.
1 2 3 4, but this hydrogen radical here is above, so that abstraction
Mhm.
won't be possible. So the answer will be option A.
Okay.
So clear?
Yes.
Okay. So yeah, this is the mechanism of swan oxidation. You can go through it if you want. Now, the correct match for the structures of the natural products in column 1 with their names in column 2. So, here four structures are there and four natural products are given: morphine, nicotine, limonene, menthol. So, can you match any of this?
Uh, the D1 is, I guess, menthol.
D1 is
No,
yes,
D is limonene. D is limonene,
yeah.
and A is menthol.
A is menthol. So, A is 4, right? A is 4. D
Yeah.
is limonene. So, which only one option is there. So, this is the structure of nicotine and this is the structure of morphine.
Morphine. Okay.
Okay. Now the next question. The major products A and B formed in the following reaction sequence. So we are treating this allylic alcohol under this titanium tetraisopropoxide L plus DET, this tertiary butyl hydroperoxide in DCM minus 20 degrees Celsius. We will get some product. Here four options are there for that, and then we are treating it with this thiol and then base, here NaOH they are using, and we will be getting another product. So which will be the correct structure for A and B?
Actually, I have no idea what this reaction is.
Okay, so what's your major?
Major as in
Like in MTech?
uh, dye stuff and intermediate technology.
Okay, that's related to chemistry.
Mostly
Okay, so you you are from chemical engineering background or?
chemical engineering.
Okay, okay. So have you heard about sharp plus asymmetric epoxidation?
I know what epoxidation is, but I don't know this one.
Okay, so epoxidation means what? We are converting an alkene into epoxide, right?
Yeah.
So sharp plus asymmetric epoxidation means we will be using some chiral ligands or some chiral source, so that only from one phase that epoxide will be forming. So that is
Hmm.
sharp plus asymmetric epoxidation. So it basically depends on which chiral ligand we are using here. So if plus DET we are using, we will be getting one particular isomer. If we are using minus DET, we will be getting another isomer. So I will say the basic principle. It is like this. So in sharp plus asymmetric epoxidation, if we consider this as an alkene in a plane, and if we consider its C phase and rephase, So if we use minus DET, attack will be from the C phase and we will be getting this above epoxide. And if we consider this, we will like plus DET, the attack will be from re phase and we will be getting this epoxide in the stereo or this configuration. So this is the basic idea of sharpless asymmetric epoxidation. Basically, we are using it for introducing epoxide group from one particular phase and we are blocking the other phase by using this ligand. So here also we are doing the same thing only. So using this plus DET, we are converting this alcohol, this alkene into epoxide. And have you heard about pain rearrangement?
No.
Okay, so pain rearrangement.
So
Yeah,
if this is the case, then the first A could be either first option or second option
first
that's
or
what these
second or first or fourth.
because this sharpness epoxidation it only attacks from one side, so
Yeah,
it has to be like in the same plane.
yes. So here as we can see, we are using plus DET, right?
Hmm.
So plus DET, if we are using what we said here, like attack will be from the reface,
So reface will be like below the plane or above the plane.
below the plane. Here, if we consider reface will be below the plane. It depends on what are the substituents. Like we will define R configuration and S configuration, right?
Huh.
So similarly, we have if it is a phase for one alkene, we will say rephase and C phase. So here this L plus DET will be giving this epoxide from below the plane.
Yes.
So either it will
Okay.
be option 1 or option 4.
Shinter.
Yeah, option 3. Yeah. Then second condition we are treating it with this tertiary butyl thiol and this NaOH. So can you guess any reaction? What can happen? So if we treat this particular epoxide, which is same as this one, with NaOH, what can happen?
NOH is a base, so it's
Yeah.
gonna abstract the proton.
Yes, so it can abstract the proton and I can write the intermediate here. So OH will be O minus and here we have epoxide. It's below, I am not writing that. Okay. Then what can happen is this O minus can attack and open this epoxide, right? So this will attack over here and this epoxide will open. Then we will be getting like this kind of some intermediate here and here this O minus will come. Is it clear? I will show it better. So if we have an epoxy alcohol like this and the base is abstracting this proton, so that negative charge can open that epoxide and can result in this particular epoxy alcohol. Is it clear?
Okay.
Okay, so this is known as chain rearrangement. So the deprotonation of the free hydroxyl group will take place, then nucleophilic attacks of that epoxide anion, and then reprotonation will take place to get this epoxy alcohol. Then what we are using here is this tertiary butyl thiol, right?
Hmm.
So what it can do is it can again this. So tertiary butyl thiol means it have this S minus ion. So that can attack over this center and it can open this epoxide and then protonation will happen to give OH here. So here it will come that tertiary butyl thiol group and here it will come OH.
OH.
Yeah.
Okay.
So what will be the product here? This one or this one?
I think the third one,
Yes, third one. So it will be attacking from this center.
tertiary butyl thiol, will like go away because of the
Yes,
base.
yes.
So
So
it's just gonna give proton.
yeah. So it will be
So
coming as
yeah,
this.
this one, yeah, that one.
Yes. So here we have discussed two named reactions, Sharpless asymmetric epoxidation and this pain rearrangement. Okay. Now the next question, which of the following dienes will not undergo Diels-Alder reaction? So Diels-Alder reaction means we should have a diene and a dienophile. So here five dienes are given. So out of these five dienes, which cannot undergo Diels-Alder reaction?
I think the second one,
Mm,
okay, second one will go under dials
yeah,
this DA reaction. Yeah, because it's
second one.
2 plus 4.
Yeah. Then
Which one will not go? The third one will also go, I guess.
yes.
And fourth one will also go. And first and fourth, I don't think so.
Yeah, but
First and fifth,
what is the reason?
because I see that it has two pi bonds.
Yeah.
So, like, the rule itself said 2 plus 4 pi bond, and then it will form a ring.
But two pi bonds are there in all of this, right? Here also two pi bond, here also two, here also two. So we are talking about diene only. Dienophile is not given here. So all of these are dienes.
Okay.
But why your answer is correct? This will not undergo and this will not undergo. But what might be the reason?
Uh, I know it, but I don't recall this one.
Yeah, so
So,
actually for a diene to undergo Diels-Alder reaction, it should be in cis configuration. So here as we can see this diene is in cis configuration, this diene is also in cis, this also in cis geometry, but here as we can see it is like this, right?
okay.
And
Yeah.
here also it is like this. So this kind of diene configurations cannot be utilized for Diels-Alder reaction. Here also it is like this, so it can undergo Diels-Alder reaction. Here it is like this in third one, and here also it is like this in fourth one. So these three are favorable, but these are not favorable. If it was not inside a ring, it can flip into cis configuration and undergo Diels-Alder. But since it is inside a ring, this cannot flip into cis configuration also. So these two dienes cannot participate in Diels-Alder reaction. Okay?
Okay.
Yeah.
Yeah.
So next question, write the correct structure of the major product in the following transformation. So this is the molecule we are treating with this lithium liquid ammonia. Which reaction is it?
I think it's dehydrogenation reaction.
Yeah, it's a reduction reaction, we can say. A name is there. Have you heard about Birch reduction?
No.
Okay, so this is an example for Birch reduction. It is basically the dehydrogenation reaction only.
Okay.
So it is electronic reduction reaction. So as we can see here, we are using this lithium and liquid ammonia. So that will generate this electron. So that is participate in this kind of reduction of this aromatic rings. So firstly, that electron will attack into one of the position. This can undergo homolysis, so here two radicals will be there. So one of the radical will combine with the electron and form this negative charge. This another radical can migrate over the entire position of this aromatic ring, and then one more electron will add up to this radical and it will form this minus charge. Then what will happen is from this alcohol, which is also required for this Birch reduction, this protonation of this particular negative charge will happen and we will be getting this dehydrogenated product. So basically we had three double bonds here, now it is hydrogenated. We have only now two double bonds here. It is not dehydrogenation, it is hydrogenation, sorry.
Okay.
Okay, so one condition for this Birch reduction is that if there are two rings in a particular aromatic compounds, more electron poor ring will be reduced first. So if I show here, so we can say less electron rich, that is electron poor ring, aromatic ring will be reduced in the case of bicyclic aromatic compounds. So if we see here, in this two rings, this particular ring is having this hydroxyl group. So due to this electron donating effect of this oxygen or OH group, this ring will be more electron rich as compared to this ring. So this
Okay.
first ring will get reduced and second ring will remain intact. But in the case of this one, which will be electron rich?
The benzene left side.
Yeah, why? Yeah, it's given here. Due to this electronegative nitrogen atom, it will be electron poor and we will be getting this ring only reduced and this benzene ring will be intact. So that's our question here also. Same only, right? So,
Yeah, so it's the first option,
yeah,
I
first
guess.
ring will be the correct answer. Only this ring will be getting reduced because it is poor in electron, not electron rich. Then the next question, identify the major products in the following transformation. So we are treating with pyridine with NaNH2 and this again that bicyclic compound with NaNH2, which will be the major products.
I think for pyridine, it's the major one will be like at the second position, third option.
Yeah, and other one?
I guess same.
Yes, but why?
Like I don't know the mechanism, but I have done this reaction. That's why I remember. Like
Okay.
this is where it forms.
Here basically what is happening, this NaNH2 is attacking, right?
Hmm.
So this like NH2 minus is attacking. So this NH2 minus, if it attacks, if I say if it attacks at this center, what can happen? This bond will shift over this nitrogen and it will form this N minus.
Hmm.
Um, then this negative charge again, if it comes back as the double bond, one proton will be there that will be leaving and result in our product. So that is a basic mechanism. So yeah, so this is a type of, we can say, a nucleophilic attack, right?
Yes.
So which will be the favorable position for that nucleophilic attack? That product will be the major one. So in the case of this one, this position, or we can say this position will be the favorable positions because of the
Yes.
presence of this nitrogen. Same with here also. Here, but one more reason is that more conjugation is in this side due to this presence of this aromatic ring. So this position would be more favorable as compared to this position.
Okay.
Okay. Then the next question, identify the correct structure of the major product in the following reaction. So this particular compound, just we are heating it at 196 degrees Celsius. What can happen?
No, I have no idea. Like
Okay, have you heard about sigmatropic rearrangement?
no.
Okay, so this is a kind of rearrangement. It's basically a thermal rearrangement. If we are treating a particular compound in with some solvent and heating it, it can undergo this kind of reaction. So if I am drawing the substrate like this, here it is oxygen, this is the double bond, and here also one double bond, and here let it be some R group. So 3 3 sigmatropic rearrangement means I am numbering it like this: 1, 2, 3, and here also 1, 2, 3. So what will happen is this 1 bond will be breaking, and there will be formation of this 3 3 bond. So what will happen is this double bond will migrate over this center, and this bond will shift over here, and this double bond will come over this position to form this 3 3 bond. So what we will be getting is here this R group will be there, here a new bond is forming, and here OH, or not OH, this double bond O will be there, and here double bond will be there. So this double bond is shifting to this position, and this 1 bond is getting broken, and that bond is basically shifting between this 1 and 2, and this double bond is shifting to form a new bond between this 3 3 position. So we will be getting here aldehyde and here alkene. This is a kind of thermal rearrangement for this kind of substrates.
Okay.
Yeah, so which is this one?
Second one.
Yeah, I know it would be little difficult for you to understand the mechanisms.
Yes.
Yeah. So, in the following equilibrium, conformer B is more stable than conformer A when the R group is. So, here are four options: methyl, fluoride, OMe, bromide. So, when it is in this particular conformation, which out of these four substituents can give more stability?
The B one,
Yes. Why?
because it's like away from the main group.
Like um, usually for this cyclohexane ring we usually say di-equatorial conformation is preferred. So if this is a cyclohexane ring, this is the equatorial position and this is the axial position.
Mm-hmm.
So for every carbon we can say like that: this is axial, this is equatorial, this is axial, this is equatorial, this is equatorial, axial, axial, equatorial, axial, equatorial. Okay, so usually we say it prefers, all the groups prefers equatorial positions only. So that is because if a group is in the axial position, it can interact with this hydrogen here. So this is a destabilizing interaction. We will say 1,3 diaxial interaction. So that is a destabilizing interaction. So that molecule will not be stable in that axial position. So it prefer to stay in that equatorial position only. So, but
Okay.
in the case of this four group, when one particular group is coming, it prefer to stay in this axial conformation. So, which group would be that?
Which will like have, which is bigger in like electronic configuration. It
It's
could be.
like if it is bigger, it will go to equatorial only. So, size is not the factor here. Have you heard about hyperconjugation?
No.
So, what will happen? The answer is fluoride. So, for fluoride, if it is coming like this, that is both the fluoride are in axial position. This is same as this B. So, what will happen? Here is hydrogen also, right?
Hmm.
So, as we said here also that destabilizing 1,3 diaxial interaction is there. But here this hyperconjugation is more prominent because of the electronegativity of the fluorine. So what will happen due to the electronegativity of the fluorine will uh, try to take all the electrons towards itself. That is, it will take this bond towards this, and this will go like this. So it can exist in this form. Here it will be F minus, and this will be H plus. So same can happen with this hydrogen and fluorine also. So this is a stabilizing interaction. Hyperconjugation is a stabilizing interaction. So this is possible only if both the groups are in anti conformation, that is diaxial conformation. So this hyperconjugation is more stabilizing, that it is actually eliminating this destabilizing 1,3 diaxial interaction here in the case of only fluorine.
Okay.
So all other groups will be preferring to stay in this equatorial conformation, but only if it is fluorine, it will prefer to stay in this axial conformation
Sure.
because of this hyperconjugative effect due to the high electronegativity of fluorine.
Okay.
Okay.
Got it.
Yeah. So now this is the last, not last, last question of week zero assignment. Major products A and B in the following reaction. So this compound we are treating with this dimethyl copper lithium and then this zinc copper couple. So what can form?
I think it's gonna break that epoxide and it's gonna form that OH.
Yes, but uh, how and which one will be the correct answer?
Actually, don't know what this line represents, the darkened one.
Okay, so this just means above and below only. So usually we write as wedge and dash, right?
Mm-hmm.
So this means it is racemic. Racemic means both the
Both
isomers are
mixing.
present, but like if this is above, this will be below, or opposite. If this is above, this will be below. So it will be always opposite, but both are present.
Okay.
So what will be the first reaction?
I think there's a lot of stereochemistry here. So either the OH hydroxyl group will be above and the other one will be below.
So yeah, which can be the answer? You are telling A or B.
Yeah,
Yeah, but what is the reaction actually? What is happening here?
I don't know.
So here one of this methyl group from this dimethyl copper lithium, Me minus, is attacking over the center. This double bond is shifting over this center and this epoxide ring is opening. So we will be getting OH and here methyl group, right?
Yes.
So that is the four options. So out of this four, whatever position this methyl group will be attacking, that will be always opposite to that of the epoxide because of the steric reason. Epoxide will be hindering one phase. So from the other side only methyl group can attack. So that OH and methyl stereochemistry will be opposite anyway. So it cannot be
Hmm.
option C and option D. Now what is the second reaction? Zinc copper couple and CH2I2. Cement Smith reaction, have you heard?
No.
So that is basically used for converting alkene into cyclopropane. I will show the mechanism. So this is the reaction. An alkene will be converted to cyclopropane. Here also we can see here this alkene is converted to
Hmm.
cyclopropane. Here this alkene is converted to cyclopropane. But from where? Like above or below or same side of OH or same side of methyl group, which will be preferred?
I think on same side as OH, like
Yes. So I will show you the reason why it is from the same side. So the correct answer is option 1. Okay. So this is the basic mechanism of the cement smith. So first the zinc copper which we are using, and this is the CH2I2. So that will form this kind of an intermediate ICH2 ZNI. Then it will attack upon this alkene and it will form this cyclopropane ring. So this is the basic mechanism. Alkene is converted into cyclopropane using zinc copper and the CH2I2. Now, what will happen if a neighboring alcohol is present? So if a neighboring alcohol is present, we can say this is an allylic alcohol kind of system. This particular reagent can coordinate with this alcohol as well. So the zinc can coordinate with this alcohol to form this OZNCH2I. Then what will happen is this only is attacking at this center. So the reaction is like this one is attacking over here and this is attacking this center. So then this OH is actually directing the attack of this particular group towards this alkene. So the attack will be same side of that of the hydroxyl group, because the zinc is coordinated with this alcohol as well and this center is attacking the alkene. So it will be from the same side only. So whichever side OH is there, same side only we will be getting the cyclopropane ring as well. Attack will be cis to the hydroxyl group.
Okay.
Okay. So that's why here the answer is first one. So first this OH and this methyl will be having opposite stereochemistry. Then the cyclopropanation will be taking place from the same side of that of hydroxyl group. Simon-Smith reaction. Now that's all about week 0 assignment. Then I have some more question. Can you try to answer this one? So this is acetaldehyde. Two molecules of acetaldehyde, if we are treating with base or acid, what can happen? You have any idea?
No.
Have you heard about aldol reactions?
Yes.
What is that?
Aldol condensation reaction.
Yeah, so what will be if, for example, if I am treating this with a base, OH minus, any base, what can happen?
It's gonna, like, if it's a base, then it's going to abstract the proton of this double bond O.
Double bond, oh, there is no proton. Okay, this proton you
Oh,
are telling?
yeah, this one, yeah.
No, actually, this alpha proton is more acidic than this proton.
Okay,
So if it abstract this proton, it cannot exist in any other form, right? So, but if we take abstract this particular proton, it will be like double bond O H. If it abstract this proton, it will be negative charge, and that negative charge can come over here, and this will go here, and that will be somewhat stabilized into an enol form. Here will be double bond, and this will exist as OH. Okay. So here there is no such stabilizing. So this proton is more, alpha proton is more acidic than this aldehyde proton. Then what can happen if it attacks abstract proton from here? A negative charge is created here. Then what can happen? So if you have here double bond O, here H, here negative charge. So we are using here two molecules, right? So
yeah,
another molecule is there, double bond O H, where it can attack.
this negative carbon ion.
This negative charge can attack at this carbonyl carbon center. This can go here, right? So
Yeah,
we will be getting here double bond O will be there, and here this is attacking over this center. So that will be converted into OH. Here I missed one carbon. One, two,
three.
yeah. So I think I have the answer. Yeah. So this OH minus will first abstract this proton. It will form this enolate, or it can exist in this form as well. Both are same only. Then it will attack over this carbonyl carbon center to form this compound. Here it will be, so this will attack over here, this will be O minus, which can be protonated to form this alcohol, beta hydroxy ketone, that is aldehyde, beta hydroxy ketone or aldehyde. Here in this case it is aldehyde.
Okay.
Okay, so this is aldol reaction. So what is the difference between aldol condensation and aldol reaction?
Aldol condensation, I think it's acidic.
No, like acidic or basic, we will call aldol reaction if it stop at this stage. If it's acidic or basic and one water molecule is eliminated, like this proton is going here and this OH minus is leaving, so one water molecule OH and this H is getting eliminated and here one double bond is forming, that time we call it aldol condensation reaction if it is basic condition or if it is acidic condition.
Okay.
Okay, so condensation means one water molecule is also getting eliminated. Next is this one. So this is a kind of intramolecular aldol reaction. What will be happening first? Sodium ethoxide is a base. So from where it can abstract proton?
Mm, from the CH3.
From the CH3. Like proton abstraction will be from the alpha position, right? So if it is like this is the alpha position. These two are the
Yeah.
alpha position. So here is C double bond O. So this is the alpha position of this
Mm,
particular carbonyl group. This is the beta CH3. And for
okay.
this carbonyl group, this is the alpha position. So either it can take from here or from here. So which will be favored?
I think where we have the beta like CH3, this yeah, that one will be favored.
Yeah, this one will be favored, right? You told this or this one?
Yeah, I thought this one will be favored.
Okay, no, because there we have to consider steric reasons also, because here CH3 is also creating a hindrance for this base to abstract this particular proton, right? But here in this case there is only two protons, there is no additional any group, so it will be more easier to take proton from this center rather than this center due to this CH3 group, which will create some bulkness.
Okay.
Okay, so firstly, sodium ethoxide will take proton from this center and form this anion, which can exist in this enolic form as well. That is, this negative charge will come over here, this bond will shift over here, and it will exist in this enolic form. And when this O minus will come back, this double bond, or we can say this negative charge, whatever forming here, will go and attack at this carbonyl carbon center. Okay, and this will shift over here and form this O minus. And when this O minus will come back, this OET is a very good living group, so it will leave. So that will result in the formation of this product. Okay, that is that they have just shown stable enolate. That is okay, both are same only. So this kind of intramolecular aldol reaction is known as Diekmann condensation reaction.
Okay.
So first proton abstraction from here and it is attacking over this carbon. So one, two, three, four, five. If five membered ring is forming, then that O minus will form. O minus when it will come back, OET will be leaving to give this product.
Okay.
The next question, this one. The major product of the reaction, this particular aldehyde on treatment with this CnCO2ET. So here also same thing is happening. Like ethanol can abstract proton from this center, then it will go and attack at this aldehyde, and that will result in like this kind of system. Here it is shown OH and the CnCO2 then elimination of water will result in this kind of product. So here it is known as Novanagel condensation reaction. These names are familiar for you: Dickman condensation, Novanagel condensation, aldol.
Yeah.
Yeah, so all these are varieties of aldol reaction only. If aldol reaction is happening intramolecularly, we call it Dickman. If aldol is happening like in this kind of system, nitrile is there and ester is there, and so this proton will be very acidic because of both of these groups. So in that case, this type of aldol reaction is known as Novanagel condensation reaction. Here also it is going and attacking aldehyde, it will become OH. Then this, as I told earlier, it is condensation. So water elimination, here H will be there, so that water molecule is eliminated to form this double bond. That is known as Novanagel condensation reaction. Okay.
Okay. Yeah.
I think that's it. This is not there. So that's it for today's session. So if you have
Okay.
any doubts or questions, you can ask.
No doubt so far.
Okay. So maybe you can join in the next week then.
Yeah, sure.
Thank you. Thank you for joining.
Okay.
Yeah.
Bye.
Bye. Maybe we can discuss two more questions since time is there. So the first one is the major product of the reaction. This particular compound, when we are treating with this amine in the presence of methyl vinyl ketone and sodium acetate acetic acid water heating condition, what will be the product? So I have given the answer here. So what is happening first with this amine? This iminium ion formation is taking place, which can exist in this enamine form as well. Then this bond nitrogen lone pairs will push over here, and this can attack over this 1,4 position. This will come over here, this will come over here, and then that can again come, and that can result in the formation of this compound. Then elimination of water, that is here alpha proton abstraction, and that can attack at this ketonic center to form this compound. So this is an example for Robinson annulation reaction. So Robinson annulation reaction is basically an aldol condensation reaction is also happening here. So that is an application of aldol condensation reaction where we are constructing a more bicyclic or tricyclic from monocyclic or bicyclic compounds. That is, we are constructing one more ring in this Robinson annulation reaction. So this is an application of aldol reaction. Then the last question for today is this one: the major product of this reaction. We are treating this particular compound with LDA in THF at minus 78 degrees Celsius, which will be the major product. Okay, so here also, as we said earlier, this proton abstraction can take place at this center and that can attack at this nitrile carbon, and that bond will shift over here and it will form NH2. Then some sort of rearrangement is happening which will form this compound, and this reaction is known as Thorpe reaction. I hope it is clear. So I will give a few minutes to go through whatever we have discussed today. And if you have any doubts or any clarifications, or if I should explain any topic once again or any questions once again, you can tell, and then we will wind up the class. So if you don't have any questions or there is no doubts, we can wind up today's session. Thank you for joining. See you in the second tutorial session, which will be on next Saturday, same time, 5 to 7, in between 5 and 7. So, hope to see you soon in the next week. Thank you for joining. Thank you.